Right, so good morning everyone, and welcome to this morning section. So we start with the talk by Vitaly Tarasov about monodromy, quantum differential equations for cotangent models of Grassmannian. Please.
So, okay, it's my pleasure to be here, and let me thank the organizers. Well, in fact, I spent reasonably long time in Japan 30 years ago, but have been here only for a short time in between. So it's just some returning to my young age, about almost half a life. Well, I'm going to talk about the monodromy of the quantum differential equation. And this is based on some joint work with Alexander Varchenko, and well, immediately just one work, but before it was several joint works which were used in this paper. And this is an attempt just to do quite elementary example from the point of view of this topics of this conference, how to understand what is going on, and to relate the things with, how to understand the relation with what is known from monodromy of difference equations from geometry, or well, for difference equation I would rather say not monodromy but condition functions from one infinity to another. And also things will go completely elementary in a sense. Well, nevertheless, computing monodromy of differential equation is still a problem, even if you know the transition function of the difference equation, which has this limit. And, well, you can see just from a couple of very, very elementary examples. So, first, if you look at this kind of stuff, well, solution is power function. Well, the corresponding difference equation solution is not well, it's meromorphic, no branching, and actually there are more solutions than here in a sense. Well, I mean, it was constant, but still there is extra parameter, well, which is related to the field of quasi-constants. And this is the first point that, well, how can we extract the branching out of, well, there is some compensation of poles and zeros to the cut, but still it's some understanding what happened. And the second, again, quite elementary stuff, well, which why difference equation might be somehow better than differentials. Well, if you look at this equation, the solution is again a power function of this kind. And for this equation, I add certain term to make things regular at infinity. Adding this term, I know how to do. I should multiply by this standard function. And this is another solution of this equation. So the first solution is regular around 0, actually in the disk, and the second is regular around infinity. And we might think about looking at the ratio of two solutions, which should be satisfying this kind of stuff, and it should be like that. But strictly speaking, if we're not doing any analytic combination, we cannot do things like that. The domains of analyticity do not intersect. However, if we look at the difference equations, then, well, one is counterpart of this is the first, this is the second. And we can write down solutions using infinite products with base Q. And then, okay, the first solution is analytic in the disk, and the second is analytic outside the disk. And, for example, in the case if we pick up Q between 0 and 1, then and A is real, then there will be some overlap of domains analyticity for A smaller than 1. And therefore, well, we can make a ratio and get that it should be the function. Well, of course, it may be situation when there is no overlap. Instead, we have a gap, non-zero gap between two domains of analyticity. But next game is just to play certain analyticity with respect to parameters, and if you can pick up a domain where there is overlap, then you have also well-defined functional parameters there, and then you can think about various analytic continuations, and well, the answer can be extracted more algebraically than in case of differential equations. So that's just elementary stuff about the problem is not completely trivial, completely senseless. So it's not just educational stuff, but a little bit more than that. So I consider the cotangent bundle of the Grassmannian and consider the action of the torus on this bundle. And the first one is actually diagonal matrices, which are acting, and the second is the dilation along the fiber. And our approach to compute the monodromy is not geometric, but rather based on some identifications and a bit of analytic stuff. It's mostly also algebraic, but there is a bit of analytic. And the point of identification is the following. First of all, we use the fact that if we pick up stable envelopes in the homology, then it's identified with the standard basis of C2. Well, identification was explained here already, so, but, well, what is important for us is a bit more, that actually, well, explicit form of those stable envelopes in cohomology, that they are given by evaluation of so-called weight functions related to quantum integrable model, namely the XXX Heisenberg chain, homogeneous Heisenberg chain. And it turns out that weight functions are exactly evaluated, they're getting exactly stable envelopes, and that, well, so as a result, well, it's extended to GLN at least, rather easily if you consider instead of C2 the space is Cn. So, and the checking is just there are formulas, and we verify that those formulas indeed satisfy the conditions for the stable envelope, so they should be. And this is our first step. And the second step is to consider the quantum differential equation, well, actually, first quantum multiplication, which I probably missed here. And we see that is the basis of stable envelopes, the quantum multiplication is translated into known operators in integrable model, the so-called dynamical Hamiltonians. And the quantum differential equation eventually is translated into trigonometric dynamical differential equation, or other people are calling it trigonometric Casimir connection. And this is the second observation. Again, it's not quite serious, but well, this was some straightforward calculation that we did comparing these two things. One taking Markov's formula and another just comparing what is known. But this identification brings us to the situation where we studied already solutions, and that's the second. And the third part is we're actually writing down some integral formulas for solution of the trigonometric dynamical equations. And I put integral in quotes because what is happening, actually there is some question of finding appropriate integral contour. because we deal with finite dimensional representation, there are certain pinchings which we should easily avoid, but we see that they do not influence. And therefore, what we basically know, we know the integrand, but how to integrate it's a little bit open question, and it's one of the technical things which are also done in this paper. And so based on all of that, and integral formulas, we are trying to compute the monodromy of the differential equation. So it turns out, looking at integral formulas, that solutions are naturally parameterized by elements of the case theory, because once you are writing down integral formula, there might be an integrand in addition to ingredients coming from just the model. There are also certain periodic functions which a priori might be arbitrary, but then certain convergence condition or whatever impose restrictions on that, and basically from those periodic functions we need to know only the values at certain points. So this naturally brings us to the case theory. And then what we are doing, we are picking up an element in, well, we are identifying certain elements. Take an element in case theory and construct two solutions with that, first of all. One we call psi x naught and the other psi x infinity. And those solutions are going to be, the first solution behave nicely in the neighborhood of 0. And then we can describe the monodromy around 0 in terms of z basis. And the second solution behaves nicely in the neighborhood of infinity. And then we can describe solution monodromy around infinity in z basis. And then it remains another problem how to relate those two bases. And basically means that we are going to make certain analytic continuation from a neighborhood of 0 to neighborhood of infinity. And that's one of the problems which we need to do. And it gives rise to certain operator in case theory, which we call transition matrix. And the role, well, see what is the role of this transition matrix in geometry. I have some conjecture which I'm going to formulate at the end, but it's not finished until here. Now, okay, let me just be in more detail so to express what is going on. So we take the cotangent bundle, we embed the Grassmannian there as 0 sections, and we label fixed points of the action of the torus by k-element subsets. Namely, for k-element subset, we take the we pick up the standard basis and consider the span of vectors with indices which are in that subset. And this span is going to be a fixed point of the torus acting on the cotangent bundle. So we consider this kind of stuff, and then we take the tautological bundle and its Chern roots, and we take the bundle of Hypersup quotients and the Chern roots there, and let Z and H correspond to the action of T. Well, in fact, just to be precise, the character of this part of the torus, this part, is actually a weight negative H, not H itself. And then, well, we have used the standard description of the homology, and basically we are putting this description as symmetric polynomials in gamma and with gamma, and CZZ modulo the relations, and relations can be written in this way. So for each y, the relation should satisfy. then we take the quantum multiplication from Mariko-Konkov and look for the quantum differential equation of this kind, where C1 is the first Chern class of E. And we are going to study it, but for the purpose to make formulas a little bit nicer, what we are going to do, we are going to slightly modify it if 2k is greater than n by subtracting this term. Then really formulas are looking a little bit nice and uniform along all the stuff. So those are our notation. Now, well, to go to K-theory, wow, typo. So then we consider variables gamma capital and variable gamma capital is an H, which has a meaning of, in the sense of exponentiated variables. So those are virtual bundles for E and variable D. And again, we are using the standard description of the K-theory as a quotient of this ring by the standard relations. And what we will, well, the K-theory of points are just Laurent polynomials in Z plus minus and H plus minus 1. We will denote the restrictions of xi to the fiber F. And now, well, I will try to describe the definition of the map tau, how it should look like in the K-theory. And then, well, I will try to explain that why this map indeed describes the transition between two bases of solutions. So, let's introduce some extra variables t, and let's consider Laurent polynomials which are symmetric in t. And in that case, we can construct two elements of the K-theory. One is obtained by plugging instead of ti just gamma i's. And the second we obtain by plugging instead of ti elements h gamma I. So from each polynomial we have two actually elements in K-theory. And what we can do, well, we consider a certain space of Laurent polynomials, which are actually polynomials in inverse variables of degree at most n minus 1 in each variable, and which satisfies certain vanishing conditions. Namely, if instead of two variables we plug z and zh, then this polynomial should vanish. The motivation to consider the space of polynomials is actually coming from integral system, because when we consider the so-called wave functions, trigonometric wave functions, then they satisfy just those conditions. And basically, if I consider this space, I can show that this is indeed spanned by those wave functions. So that's somehow natural. On the other hand, this space arises naturally when we are analyzing integral formulas for solutions, because this way, well, the restriction on degrees comes out from the convergence of integral formulas at infinity of integral contour. And this condition comes out as a certain condition which allows to make some, say, pinchings or whatever without breaking the convergence of integral. We can go through that, at least morally. So the formulas will not use that, but morally we can go through this kind of pinchings without changing the integral. So those are conditions, and for those conditions we consider the corresponding classes P gamma and PH gamma, And it turns out that for each polynomial satisfying those conditions, the corollary is that those classes are divisible by the class E of gamma H. Well, I probably write this definition of the function E. Yes, so here's the definition of the function E. So E is a function of variables t, which is the product of all pairs I not equal to j, 1 minus h ti divided by t. So in principle, if you include I equal j, then there will be the factor like 1 minus h, but we do not want to see those factors, we want to see only things like that. And it's indeed symmetric on all t's, because both pairs appear here. And, well, if I consider, so substitute gammas instead of t, this is some kind of Euler class, and this condition shows that this is always divisible, so there are other classes which are coming from this formula, so those classes I will denote by p naught and p infinity, and they define projections from this space to the case theory. And the proposition, not so difficult, but requiring a little bit of work, is saying that those projections are actually isomorphisms of C AT of point modules. So of course, both spaces are those modules, so this is like. And then we defined the map tau in this way, like P naught inverse P infinity. So we are going to take an element from KT, raise it to P, and then put it there. Well, of course, if I take just polynomial P and divide by E of t, it's a rational function. So this condition does not show that this is a polynomial, but once we are going to case theory, they are going to be one divides us. Well, you can calculate the determinant of this map, and the determinant has a rather nice formula, though the definition involves z. Like essentially, the determinant doesn't depend on z. So actually, tau and tau inverse both are inappropriate basis. Those entries are Laurent polynomials in z and h. And moreover, if the basis is indeed tuned well, so for instance it can be stable and well basis, then actually those matrices are Laurent polynomials with integer coefficients. Okay, now I'm going to explain some ingredients of integral formula for solutions. And first I continue with trigonometric functions. So I consider the so-called trigonometric wave function, which is obtained by taking this kind of product and then symmetrizing it. Well, we call it reduced. And then to get the weight function W naught, we multiply this reduced by this product, and to get W infinity, the opposite weight function, which we called it there, we multiply by this kind of product. Well, those functions are actually related to weight functions in integral models, now in XXZ model, and those are certain specific wave functions with extremal indices, with appropriate order of these. And once we're going to specialize, we're going to produce some specific stable envelope, trigonometric stable envelopes. So a bit of notation, so Z sigma means that I just interchange all Z. And then the proposition shows that both those functions, whatever order of Z I putting in the definition, are going to be elements of this space. So the polynomiality and degree is not so difficult, well, but the condition of vanishing is a little bit of that, but also rather straightforward. And then let me introduce this other kind of functions. And the important property of those functions W, which appears, is that they actually produce the inverse maps by 0 and by infinity inverse by certain explicit formulas. Namely, if I want to compute by naught of inverse of x, which I will denote by this function in this way, then it's going to be summation over restrictions with that stuff, and also the same for infinity. So it gives explicit formula for the projections, and therefore eventually we can get explicit formula for the map tau in terms of the weight function. Also, okay, let me see. The summation over. Yeah, so this should be, well, I guess there is typo here, should be definitely the I, and that's probably should be okay, and this is also the I, right? So I put it in just inside the sum, but it can be taken out. But the point is that, well, since those are elements of the space P, then we know that putting here the I, we're getting, it's basically the same as computing in K series. The result will be divisible by that. So actually result is given by Laurent polynomial. There is no denominators of this kind. There is consolations. And this formula essentially explains that this is indeed Laurent polynomial, and the coefficients can be done integer, and it's also used to compute the
Richard,
Yes.
can I ask a question?
Yeah.
Is this last formula related to the
Which one?
this formula for tau x? Yes. Is it related to the orthogonality of wave functions?
Well, this is orthogonality of functions which are introduced, but it is not orthogonality of the standard wave functions which are stable invariants. Because the function which I wrote down, once you compute, those are, well, if you fix, say, the standard sigma, which is identity, then this is in a sense, well, some extremal stable envelope, where you are taking the subset either 1k or z. And then what I'm doing, I'm not changing subsets further, but I will be changing chambers. I pick up the same stable envelope in this sense, but for different chambers. And this is related to the fact that, well, functions W and functions W infinity, when you make a basis by changing chambers, still are making an orthogonal basis. This is other kind of orthogonality. So trigonometric wave functions are part of the formulas for integral formulas for solution, but of course the more essential part is going to be rational wave functions. Rational wave functions appear in integrable models, well, wave functions in general, as coordinates of certain vector valued functions which were in a sense, some technical tool. Well, when we are saying this ansatz, we never understand why this is ansatz nowadays. But originally, what is happening, then indeed it was certain ansatz for the form of eigenvectors as values of certain function at certain points. And wave functions are coordinate of this vector valued function which is used in the ansatz. And that's how they appear in integrable models. Well, this is a rational wave function, but it's already translated to cohomological language. So initially, well, what we have certain functions labeled by subsets, and we multiply by the standard basis and sum up and get certain vector valued function. And, well, the coefficients of that function are, in what happens, well, stable envelopes are in variation of one kind of wave functions, and the coefficients which I need are the functions which will be giving the stable envelope for the opposite chain. But here I'm summing up not two stable envelopes, but one of stable envelopes is replaced by a function. But nevertheless, it turns out that that summation is going to be, can be performed, and the result is basically going to be the first stable envelope, but where the equivariant parameters are replaced by Chernowitz. But dependence of the variable t just as it should be. So this class can be computed instead of the sum, it can be just computed symmetrization of the product. Well, there is also another part. This is, I was saying, it's reduced in a sense. There is another part of the calculation which does not depend on t, but actual wave function will be the product of this and q. But this does not depend on t, so it will be just always appearing as an extra vector.
So, excuse me, do you know, so if you don't have that gamma tilde, then
Yeah.
that's the,
What then we do not have. So I'm writing down the function with values and cohomology.
I mean,
Function of t with values and cohomology. So what do you mean if we do not have? If we just remove this factor, what?
so if you don't have gamma tilde, it's the matrix elements of the B of the offshore vector of the x-axis.
Well, in the language of integrable models, there is no such formula without summation. This is the image of what we call vector valued. So indeed you are applying B to the highest weight vector, and you look for vector valued function, not for coordinates. And when you are sending it to cohomological level language, well, the coordinates there, they are functions of t and z, which are equivariant parameters. And the standard basis is going to the stable envelopes, which are the elements of cohomology, and you sum up all the stuff. And it turns out that the result of summation, well, can be computed explicitly. It's looking like
Yeah,
that.
no,
So
but
it's,
taking matrix elements is encoded into I.
well,
Larger.
so there is no I in this, well, there is no subset in this function. If you want to compute well, something depending on subset, what you should do, you should just compute the restrictions of this cohom. Evaluate this cohomological stuff at fixed points. You should give values for gamma and gamma tilde from the set of these. So this is just, well, for each choice of t's, this is element of cohomology, this is the homologically valued wave function. And this is the master function. Well, here there is no classes, there is just equivariant parameters, and it's actually symmetric in Z. So And this is our choice for master function in this particular case. And then to, well, maybe I should say a few words. So then to compute a solution, basically what we are going to do, we multiply the master function and we multiply it by the main function. And if we apply here differential operator, then the result will be somehow certain discrete differential, and we need to compute certain functional which will eliminate all discrete differentials. And there are a couple of ways of doing that. One way is just to compute the series with appropriate step, and the second way is really to compute an integral such that after the shift the contour can be written back, and then there are certain equations of convergence. When we are writing down the integral, then it becomes important the behavior of as functions of t, and the good candidate here might be some deformation of imaginary plane. But then at imaginary infinities, it turns out that if I simply multiply phi by w, well, w is a polynomial, so it's not much. But here we will see that asymptotics are such that, well, the integral cannot converge. So we need to multiply actually by certain periodic function, trigonometric, which will adjust asymptotics. And in general case, when equivariant parameters are generic, well, we can just pick up those restrictions on dependence on periodic function as Laurent polynomials and exponentiating variable. So, but here we are first prefer to consider series. So we take and sum up those residues. So this is series in P, and it's behaves nicely for P smaller than 1. It's really analytic function for P smaller than 1, and this is analytic for P greater than 1. And then to make the solutions, we multiply them just by certain powers of P. And then this function which behaves nicely around 0, this behaves nicely around infinity, and they can be distinguished by those exponents for generic Z just by eigenvalues of the residue of differential equation at 0 at infinity. And those are labeled by subsets, and to get solutions which are labeled by cohomological classes, what we are doing, we are taking a class, we plug there instead of variables exponentiated of Z, T and H, and of Z and H, and then sum up those with the values which are just evaluation of restriction of classes with fixed points, and then we get those solutions again of nice behavior. And those solutions turns out, well, they have a little bit better analytic properties in Z and H than psi i's itself. There is some regularization due to summation. And then, well, if we think about monodromy around 0 and around infinity, then what is happening? That for this solution, the monodromy is described that it should take class and multiply it just basically by determinant of topological bundle. And at infinity, you multiply again by similar stuff, and h in power k. Well, but this is for opposite, in a sense, orientation of the circle, because, well, really I prefer that these circles are oriented the same way around 0. And therefore, those are two basis that we are going to use. And then the next stuff is, well, we are going to see an integral and compare those two bases. In this case, well, as in our elementary examples, those functions are defined, well, on a universal curve, in fact, because of some fractional powers, but essentially it's a disk p smaller than 1, and this is for the disk p greater than 1, and there is no intersection of domain of analyticity. So we need such a formula which will allow us to make a continuation from one domain to another, and this is what we are getting from integral stuff. So we take this kind of integral where the part master function and w is, well, some standard which we have for the integrand, and this part also standard, well, it's determined by the differential equation, but this u and this e are going to be periodic functions. They obtain from the product u, which we had before, for trigonometric wave functions, and from the function e by replacing capital variables with exponentials of small variables. This is a periodic function, but it's, first of all, it has something poles, and second, well, we should, well, it somehow grows or decays at infinity, and the power, well, the formula for that tells us that at infinity the things are fine, the integral is convergent, but there are certain poles, and to avoid that, well, we need to make this contour specific. That's the trick why we are putting just the product and not the symmetrized things, the trigonometric wave function, because if you put really symmetrized, then there will be certain trouble with the integration contour, but if you put a product, then depending of which order of z's we will picking up, well, here it's important that I take the standard order of z's, I can make rather simple choice of integration. So I get out of this formula, after multiplying, just one solution, not many, because really, well, the order of this fix me how this contour should be done. This is a collection of imaginary lines for each variable, but they are somehow ordered to avoid poles. But how to get other solutions? Well, I can simply interchange these. It will affect, of course, this part. It will affect also the contour, but since this part is symmetric in z, well, it still will be a solution by the same reasoning. And, well, therefore we have a basis of solutions by taking this function and making, not a basis, but we have many solutions at least by changing these. And then what we can do, we can take this integral and compute it by residues, either to the left or to the right. And the simplicity of integration contour allow us to do that. Not immediately, but with certain more or less standard work. And then we are getting some solutions corresponding to certain case theoretic classes. Well, there are certain sums of series, and it turns out that in one case this class is pi naught of this function, and in this case it's pi infinity of this function. But by definition, well, now we see that if we pick up this solution, it goes to be like that, and then it goes to be like that. This solution is actually defined for p smaller than 1, and this is for p greater than 1, and if we analyze what is happening with the integrand, then it's defined whenever this term does not break converges at infinity. And therefore restrictions here on P is not on absolute value but on imaginary part. So absolute value can be arbitrary because it brings just oscillations, but imaginary part controls the decay, and therefore this stuff is analytic in a certain strip with imaginary part, or the strip of width 2 pi for imaginary part. And therefore those two things have intersection of domains of analyticity in those two, and therefore it gives us analytic continuation, and by definition we can say that, well, this solution, well, that we can verify, that's actually by definition, that this is of tau is true, and therefore we observe that for those solutions we indeed know that analytic continuation is given by tau. And we can do it not only for identity, well, we can do it for any commutation, and we can see that those are really bases of solution, bases in K-theory, and therefore it proves the result that transition function from 0 to infinity is, or transition function between two bases of solution is governed by this net tau. Well, now, what is the meaning of this tau in K-theoretical stuff? Well, immediately there is nothing, but what can be verified basically then, first, the tau is actually the transition between stable envelopes for the case theory of this Grassmannian with given, well, in this case, I guess antidominant alcove and standard chamber, what I choose. But we can make two the stable envelopes in the case theory for the dual Grassmannian, and for the opposite choice of alcove, and for the opposite choice of the chamber. Well, that's, for me, it's just the matter of certain calculation, which is based on matrix properties of wave functions. Well, it's possible to evaluate, to check that the evaluation of wave functions are basically of the same matrices with the same triangularity and the same recursion properties, so they should be the same. And therefore, okay, well, then the last remark, if you look at monodromies around 0 and around infinity, then those multiplication by determinants after certain loop can be interpreted as transition matrices of stable envelopes between not exactly neighboring alcoves but sufficiently close to each other, obtained by certain elementary translations. Also, yes.
Is there a conjecture, or you can?
No, for for SL2 it's not conjecture, it's actually I checked, but it's not in the paper, it was done later for Grassmannian. But, well, it actually should be true for partial plug varieties, and I have some ideas how it should be proved to reduce to Grassmannian, but it's not done. Thank you.
Right, are there any questions?
So, thus obtained the transition function or transition matrix somehow related to R matrix also.
No, this is not a matrix, because we make a change of, well, if you think about trigonometric matrices, integral models, then what happens, we are picking up the wave function for the wild reflected weight subspace, and for actually not for exactly the same matrix. And we are going to compare their values. Because we cannot compare the functions, they have even different number of variables. But we can compare the values, the evaluations. So it's not kind of, well, it's another kind of, probably geometers will call it still a matrices, various transitions, but this is not exactly the standard matrices. Those are other.
Level and one.
Well, not exactly, because I don't know.
That switches the to Grassmannian.
Well, that's rather related to maybe some kind of mirror duality. Well, on representation point of view, it tells that the monodromy of dynamical equations should be given by some kind of affine Weyl groups here of trigonometric. Well, actually for SL2, the monodromy of trigonometric SL2 connection was computed by Redana, Lared and Galton some time ago, but I discovered that paper only after finishing that. And they did a lot of work on monodromies of rational cosimic connection, but trigonometric, I didn't understand how much they, well, they claimed that they did everything by, if at least can reduce anything to SL2 case, but, well, I should read more carefully what they did.
Perhaps it is related to so-called wall crossing.
What?
No? Wall crossing formula.
What kind of formula?
Yeah, so it's a transition from Grassmannian Kn to Grassmannian N minus K. And it's a chamber.
I didn't work out much of that. Well, I made this observation after completing the paper, but I didn't work much. So I cannot comment. But this is in a sense elementary exercise, and perhaps maybe many things might be known already.
More questions? Maybe I can ask or add something. So it looks to me like the last conjecture, the Grassmannian of n minus k is what we get if we consider that this is a pure variety with opposite stability condition. Right? So your conjecture says that your transport of quantum differential equation maps stable envelopes from a pure variety with positive stability condition to a stable envelopes to stable envelope classes in a pure variety with opposite stability condition. And in a sense, that's probably like
But also with some change of chamber probably as well.
well, with some appropriate changes, yeah. And another way to
Perhaps, yes. So that's maybe the right way to say it.
that's one thing. This, like you described how the monodromy around zero looks like, and monodromy around infinity looks like. In both cases, it's like multiplication by O1, but at infinity, it's also shifted by some extra power of far. And this is just O1 on a Grassmannian with opposite stability condition, so it's kind of matches. Okay. Maybe the last thing you said that monodromy around zero at infinity acts by like a simple shifts. And the simple shift corresponds to like the shift of a slope in a stable envelope, right? I guess even for Grassmannians, like the set of chambers, they are not quite they cannot be obtained from one single chamber by the action of shift by line bundles. So general.
That's right. I'm saying it's not maybe neighboring. It's maybe.
Yeah. So what is the choice of a general chamber in your pitch? How you see it?
Oh,
slope of stable envelope?
for the moment I'm starting probably from anti-dominant chamber, just that's what, well actually, actually in Grassmannian probably just even and odds can be obtained from each other by shifts. And to go from odd to even, I need to do some reflection.
Right. Well, if there are no more questions, let's thank the speaker again.
Andrei, time for the next.
I forgot. So we have 15 minutes break, and so we meet here at 11:15.
So as I have already told you that the next room, but that is in what? No. So stay outside of the engagement. Great. This side, I don't know the reason, but today this